Hi, everybody. It's Professor Mitchell. Today we're talking about 6.1, the law of sines. And the objectives in this section, use the law of sines for a couple of different things. And then there is a related formula that you can use to find the area of a triangle. Okay. All right, so what 6.1 and 6.2 have in common is that we are going to use them to solve oblique triangles. So far, the only kinds of triangles we know how to solve are right triangles. So oblique triangles do not contain any right angles. Either it has 3 acute angles or it has 1 obtuse angle and 2 acute angles. Okay, so these are what oblique triangles look like. And you can use the law of sines or the law of cosines to solve those. Remember, solving a triangle means find all the sides and find all the angles. And of course, some of the sides and or some of the angles will be given. Okay. All right, now, one approach to this, and this is the approach I don't like, is for you to sort of memorize, okay, what are the situations where I can use the law of sines and what are the situations where I can use the law of cosines. But I don't think you really need to do that because here's what the law of sines says, and I'm not going to try to prove this or anything. I'm not sure I remember how, all right? But if A, B, and C, capital A, B, and C, are the measures of the angles of a triangle, of any triangle, and little a, B, and C are the lengths of the corresponding sides. By corresponding, I mean opposite. Little a is opposite angle big A. Then these 3 ratios are all equal. Little a over sine A is equal to little b over sine B, and those 2 are also equal to little c over sine C. Okay. And you're going to see that again on the next slide, because on the next slide I'm going to talk to you about when can you use this. All right. The law of sines is, I think, a little easier to use than the law of cosines. So you always want to try to use the law of sines if you're given the right kind of information. So basically, you need, in order to use the law of sines, you have to have enough information to complete one of these ratios. They either have to come right out and tell you one side and the measure of the opposite angle, okay? And then they have to give you at least one of these other things, all right? So let's see, how does that translate into this? So the 3 known measurements can be abbreviated using SAA, which means that you're given a side and 2 angles. So if you have a side, let's say A, and you have any 2 angles, all right? If you had big A and big C, that would be enough, because having big A would complete this ratio. Same if you had big A and big B. Or even if you had little a and big C, because if you have angle B and angle C, then you can use the fact that the 3 angles have to add up to 180 degrees, right, to complete this other ratio. Okay. And then the other situation, well, and basically that's it. So SAA, which is a side and 2 angles, or ASA, which is 2 angles, and then it has to be the side between them. So let's say big A, big B, and side C, for example. Okay. So in either of those 2 situations, you will be able to complete one of these ratios. And if you're given at least one of these other things, then you can knock out all 3 of them. Okay. So, are we ready for an example? I think we are. So in example 1, they want us to solve the triangle where big A is 64 degrees, big C is 82 degrees, and side C is 14 centimeters. So the first thing I want to do is show you a picture of that. That looks like this. So let's see, this is SAA. This is what they call SAA. You're given a side and 2 angles. Okay, the side is not between the two angles. So in this case, we have enough information to complete the ratio about C. Okay, but before they do that, they're going to use the fact that the three angles add up to 180 degrees to find angle B. So if A plus B plus C is 180 degrees, we have A, we have C. So now you have enough information to solve for B. 64 degrees plus 82 degrees is 146 degrees. Subtract 146 degrees from both sides. You get that angle B is 34 degrees. Okay. So now we have all three angles. So the next thing I'm going to do is I'm going to use the fact that I have angle C and side C. I'm going to plug those into my law of sines ratio, and I have angle A, right? So the law of sines says in part that little a over sine A is equal to little c over sine C. So I'm going to plug in side C, I'm going to plug in angle C, and I'm going to plug in angle A. And what they like to do is first cross multiply these things. Let me just remind you how that works. So when you have a proportion, and this is an example of a proportion, two fractions that are equal, you can cross multiply those to get an equation that does not involve any fractions. So if you multiply those together, you get that A times sine C is equal to C times sine A. Okay. And what do I have again? I have big A, I have little c, and I have big C. So that's enough information to solve for little a. Okay, so solving for little a, and what did they do? They divided both sides of this equation by sine C. They get that little a is equal to C times sine A over sine C. Little c is 14 centimeters, big A is 64 degrees, big C is 82 degrees. You plug that all into the calculator and you find that little a is about 12.7 centimeters. All right, continuing with example 1. We have now found angle B, we have found side A, so the only thing left to find is side B. So once again, we're going to use the law of sines for that. And they decided to use the ratios that are about B and C. We could have just as easily used B and A, because we know everything there is to know about C, we know everything there is to know about A. Okay, so, and they are going to cross multiply again. They're going to multiply side B times sine of C and equate that with side C times sine of B, which looks like this. And now since we are trying to solve for side B, we're going to divide both sides of this by sine C, and that is going to give us something good. That's going to give us C times sine B divided by sine C. That comes out to 14 sine 34 degrees divided by sine 82 degrees, which is about 7.9 centimeters. All right, next example, solving an ASA triangle, which is kind of similar. So they want us to solve triangle ABC. If angle A is 40 degrees, angle C is 22.5 degrees, and side B equals 12. Round measures to the nearest tenth. So if you're watching at home, I'll ask you to pause the video and try this one yourself, and then we will come back and compare notes. All right, let's compare notes. So the difference between this problem and the last problem is that you absolutely have to find angle B first, right? Because these three pieces of information are not enough to complete any of the ratios in the law of sines. So I need to find angle B, and then I'll have a complete ratio about B, right? So there's a picture of this triangle that looks like a pretty decent picture. The three angles add up to 180 degrees. A is 40 degrees, C is 22.5 degrees. That means that angle B is 117.5 degrees, right? Okay, so it's your choice of what to find next. We have all three angles, so we could either find side A or side C first, and it looks like they decided to go with A. So again, we'll cross multiply these two, and that'll give us B sine A equals A sine B. And since the thing that we do not know is side A, we'll solve this equation for side A, which gives you this. Side B is 12, angle A is 40 degrees, angle B is 117.5 degrees, which makes side A about 8.7. All right, so far we have angle B is 117.5 degrees. We have side A is 8.7. Now we have to figure out side C. So they're going to use these two ratios. They're going to cross multiply them. And now they are going to solve for little c, because little c is the last thing I don't know. So little c is going to be B sine C divided by sine B. You plug everything in, and that comes out to be about 5.2. And I don't feel bad about leaving out the units on the sides because they did not give me the units for side B. So that's the best we can do with that one. All right, that brings us to my favorite thing, which is called the ambiguous case, SSA. That's where you're given two sides and an angle opposite one of the sides. Depending on the size of those numbers, that information may result in one triangle, like we've been getting, two different triangles, or possibly no triangle. Okay, and that's why it's called the ambiguous case, because I don't know exactly how many triangles will come out of those specs. Okay, so what I'm going to show you now are some pictures. It is really not worth trying to learn all the relationships from these pictures, because if you just take the numbers they give you, pretty soon you can figure out which situation you're looking at. Okay, so the first situation is one triangle. That looks like this. So they give you, let's say, side A, side B, and angle A. If side A is greater than the height of the triangle and is also greater than the other side that they gave you, that will give you exactly one triangle that looks like that. Okay. Okay, this is another example of one triangle. It happens to be a right triangle. That's if side A is exactly equal to H. Here is the no triangle situation if side A is less than the height of the triangle, because then it's not long enough to complete the triangle. And you will see here in just about a minute what that looks like when you try to use the law of sines. And then my favorite situation is this one. A is greater than H, but less than B. In that case, you get two different triangles. You can see them right here. Okay, so let's start with the no solution case. What does that look like? If angle A is 50 degrees, side A is 10, and side B is 20. Okay, so I'm going to use this proportion, right, because I have everything I need about A, and I have side B, so that should be enough to complete this proportion. As usual, they're going to cross multiply, and since I don't know angle B, I am going to solve this equation for sine B. I think that might be worth scribbling something in here. So we're going to divide this equation both sides by little a. Okay. All right, so that's going to give me sine B is equal to B sine A divided by A. And when you plug in the numbers, it turns out that sine B is about 1.53. And if you think about that for a minute, hopefully you can see what's wrong with that. It's been a little while since we've talked about this. Think about the range of the sine function. What kinds of numbers can come out of the sine function? Only numbers that are between -1 and 1, remember? So, and if you forget that, all right, you know, sine B is about 1.53. So what we would normally do here, even if that was a number that made sense, is we would use the inverse sine function to figure out what this angle is. And if you ask your calculator what is the inverse sine of 1.53, it's going to give you an error message, okay? Because there is no angle whose sine is 1.53. So this is a no solution. If you try to draw this triangle, it will not work out for you. All right, that brings us to example 4, solving an SSA triangle, the ambiguous case. And in this one, there's going to be 2 solutions. So how does that work? They want us to solve triangle ABC. If angle A is 35 degrees, side A is 12, and side B is 16. Okay, so they've told us everything there is to know about A, ratio A that is. So we'll go ahead and figure out angle B, or try to figure out angle B. So cross multiplying, you get the usual. Solve that for sine B, just like in the last example. You get sine B is equal to B sine A over A, which comes out to be 0.7648, which is within the range of the sine function. So there is an angle that has that sine. So to find that angle, we will take the inverse sine of 0.7648. Now remember, just a little flashback about the inverse sine function. Inverse sine will always give you an angle between -90 degrees and 90 degrees, right? We always said at the time between -pi/2 and pi/2. When you're doing this kind of solve the triangle problem, this thing is never going to be negative, because this angle here will always be, let me think about this for a second. Well, it'll always be between 0 and 180 degrees, right? So the sine, S-I-N-E part will be positive. So this thing will always be positive, which means that one of the angles, or I should say the angle that you'll get out of the inverse sine will be an angle between 0 and 90 degrees, okay? Now, what makes this so interesting is that we have to allow for the possibility that, that angle B is 50 degrees, or there is another angle whose sine, S-I-N-E, I don't know what I was starting to spell there, is also 0.7648, and that would be the corresponding angle in quadrant 2. Okay. There are 2 angles between 0 and 180 degrees for which sine B is equal to 0.7648. One of them is 50 degrees. And the other one will be the supplement of 50 degrees, which is 180 minus 50. Okay. Okay, so far we found that one possibility for angle B is 50 degrees. The other possibility is that angle B is the supplement of 50 degrees, which is 130 degrees. Now, as I was just telling the class that's sitting here in front of me, sometimes it will make sense for a triangle to have this angle A and the larger choice for angle B. Sometimes that will make sense, and sometimes it won't. So the way that you tell whether or not it makes sense is by adding those two angles together, angle B and the two choices for angle A and the two choices for angle B. Make sure that they don't add up to more than 180 degrees. All right, sometimes A plus B2 will be more than 180 degrees, and when that happens, you can just throw it out because there's not going to be any triangle where two of the angles add up to more than 180 degrees, right? In this case, they both add up to be less than 180, which means that there are triangles that have these specs right here that were given and have either one of these choices for angle B. So what we have to do now is find both of them. Okay, so continuing with example 4, let's see. Okay, so now we're working on finding the first version of angle C. They're calling it C1. This is the one that goes with the 50-degree angle for B. Okay, so the way that you find that angle C is the usual. You use the fact that the three angles have to add up to 180. So in this case, A is 35 degrees, B is 50 degrees, which means that C will be 95 degrees. And now we will use our law of sines ratio to find side C. Actually, first we're going to find the other version of angle C. I can never remember the order that they do these things. We could have found the first version of side C next, but they decided to knock out their two possibilities for angle C first. Okay. So the other possibility is that angle B is 130 degrees, and in that case, angle C would be 15 degrees. It would be a very small angle. Okay, so I kind of think of this as a split screen. Let me see. I'm hoping this will work out. All right. So one possibility is that angle B is 50 degrees and angle C is 95 degrees. That's what we just did. So in that case, we'll use the law of sines ratio to say that B over sine B is equal to C over sine C. Notice they're being very careful with their subscripts, which is good. We'll cross multiply. And now the unknown thing is side C1. So if we divide both sides by sine B1, we get this. And my split screen almost worked out. B sine C divided by sine B will be 16 sine 95 degrees divided by sine 50 degrees, which is about 20.8. So in a world where angle B is 50 degrees, side C will be 20.8. And then the other possibility, doing it the same exact way, only now with C2, you get that unknown side C2 is equal to, again, B sine C divided by sine B. Only this time, angle C is 15 degrees and angle B is 130 degrees. So in that case, unknown side C will be about 5.4. Okay, so here's what we found. If angle A is 35 degrees, side A is 12, and side B is 16, then one possibility is that angle B is 50 degrees, angle C is 95 degrees, and side C is about 20.8. The other possibility is that angle B is 130 degrees, angle C is 15 degrees, and side C is about 5.4. All right, that brings us to the area of an oblique triangle. I think that you can actually use this for any triangle. It's just that it's much simpler if the triangle happens to be a right triangle. Remember, oblique just means not a right triangle. Okay. All right, so I am not going to read this in words because, again, I don't think it's helpful. There are 3 different versions of this depending on what information you have. the area of a triangle can be found by taking 1/2 the product of two sides and the angle between them. And basically that captures all of these. 1/2 times the product of two sides times the sine of the angle between them. So that angle could be either A or B or C. All right. And again, depending on what information you have, will tell you which version of this to use. All right. So here is an example of finding the area of a triangle. They're telling me two sides have length 8 meters and 12 meters and have an included angle of 135 degrees. So they did not suggest any particular labeling, you know, in terms of A, B, or C. They're leaving that up to me. Here's a picture of that triangle. So they decided to call the given angle C. So in the version of that formula where where angle C is given, it goes 1/2 AB sine C, right? So we're going to use that version of the formula. A is 8, B is 12, or the other way around, it doesn't matter, times the sine of 135 degrees. We happen to know the exact value of sine 135 degrees. It's √2/2, right? But they're telling us to round it to the nearest square meter, and so we could just ask the calculator. And it turns out that comes out to about 34 square meters. All right, that brings us to our last example for law of sines. This is an application problem. Two fire lookout stations are 13 miles apart. Station B is directly east of station A. Both stations spot a fire. The bearing of the fire from station A is north 35 degrees east. And the bearing of the fire from station B is north 49 degrees west. And that is enough information to figure out how far to the nearest 1/10 of a mile is the fire from station B. So what you should try to do, before I uncover it here in a few seconds, is try to draw a picture of that. Use what you remember about bearings and how they work. And when you draw that picture, it should come out looking something like this. Okay. So the bearing from station A to the fire, so the fire is at, and I am not going to try to draw a fire. I can barely write the number 2 sometimes. Okay. We'll call that a fire. How's that? Okay. So the bearing from station A to the fire is north 35 degrees east. So remember the bearings talk about, is it in the north or the south direction? And then how many degrees from the vertical do you have to go? Okay. So this angle is 35 degrees, and then the same thing coming from station B, it's north 49 degrees west. So that would look like this. Okay. So notice that that does not directly give you either of the angles in the triangle that we're going to end up using, but you can pretty easily figure those out, right? This angle and the unknown angle A will add up to 90 degrees. This angle and the unknown angle B will add up to 90 degrees. Okay. So, yeah, so angle A is 55 degrees because those two angles have to add up to 90. Angle B is 41 degrees because those two angles have to add up to 90. So what do we have? We have two angles and we have the side between them, which is side C. So as long as we have two angles, we can definitely use law of sines because now we can find the other angle and then we'll have a complete ratio about C, right? So now I will find angle C by using the fact that those three angles have to add up to 180 degrees. Turns out that angle C is 84 degrees. Okay, so now we have all three angles. I don't know why they only labeled A and B. We also know angle C is 84 degrees. And that's what we're going to use. That is the complete ratio we have. It's about C. So now let's see. We're trying to find the distance from station B. And that distance is called A, isn't it? And it's not because we're trying to be confusing. It's just because that's the side that sits across from angle A, and that's the one we're trying to find. Okay. So one good thing about these application problems is that you usually don't have to solve the whole entire triangle. You can just, you know, find the thing that you need. So we're not going to bother finding side B because they didn't ask for that. So we have everything we need about ratio C, so we'll set that equal to ratio A. And we will cross multiply. And we will solve for little a. Little a is C sine A divided by sine C, which comes out to about 10.7. So this fire is about 10.7 miles from station B.